Okay, so what we're doing is using Venn diagrams and applying the rules of probability. So there are rules in your formula booklet, right? Page about 60 or something, really early on. Right, so the rules for probability. For those of you that did have it in IGCSE, this will be easier. Those that haven't done it, which is the first one. It's not a difficult thing. So, we've got certain rules, like the probability of A happening, right? Or the probability of B happening, right? You find that by doing what operation? The probability of A plus the probability of B is what I mean. By an operation, do you add or whatever? Okay. Right. Another way of writing probability of A or probability of B using Venn diagrams. So if we had a little Venn diagram, okay, if this was true, if I had A happening and B happening as two separate things, in this situation they are called what events? Anyone know? Did you just say me?
Yeah.
Me, but with a big gap. Yeah. Mutually exclusive. Yeah. Okay, so basically, when we've got mutually exclusive events, you've got two events that don't overlap at all. So they can't both happen at the same time. So, for instance, if I was going to roll a dice, all right, I could have the probability of a 1 or a 3 would be the probability of getting a 1 plus the probability of getting a 3. But they are mutually exclusive because we can't roll a dice and get a 1 and a 3 right, at the same time. Right? So that would be 1 over 6 plus 1 over 6, which equals 2 over 6, okay, or 1/3. They're mutually exclusive. However, using Venn diagrams explains the next thing quite nicely. If they're not mutually exclusive, right?
Which would be what? What's the word?
So if we say probability of A or B again, but they're not mutually exclusive, is when we have this situation with a Venn diagram. We have an overlap. So if they are not, I'm going to use my shorthand, not mutually exclusive, is when two things can happen at the same time. So if I roll a dice, for instance, and I say to you, what is the probability of getting a 2 or an even number, right? What do you notice about 2 or even?
Oh, 2 is an even number.
So 2 is also an even number. So I can roll a dice and get a 2 and have an even number at the same time. Alright? So therefore, if set A is all the numbers and B are even numbers, okay, so a 2 would be in there. Okay? The even numbers would then be 2, 4, 6. Okay? And actually set A being 2, that's it. The rest of them would be 1, 3, 5 would be out there. Okay? So actually A would be 2, being a 2. Right? So actually, technically, this diagram would look like this. B and A would be a subset. Right? If I chose a different situation, like could I do? If I said probability of even or prime, what would be the probability of getting an even number or a prime number from a dice? So even numbers being A, prime numbers being B. So the even numbers are 2, 4, 6 and 8 again, or 2, 4, 6 on a dice. B being prime numbers, the prime numbers are 2, 4 and 6 are not prime. B would also be, what would also be in B? The prime numbers. 5 and 3. So the only one not in there would be a 1. 1 wouldn't be in either of those groups. So the probability of getting an even or prime is this 2. Right? But if I were to do the probability of even plus the probability of prime, well, that would be the probability of even is 3 out of 6, plus the probability of getting a prime is 3 out of 6. If I add those together, I would get the answer 1, which would make it certain that I have to get an even number or a prime number. But is that true? No, it's not true, because I know 1 is not in that, so it can't be certain, so there's something wrong. Exactly. So because it's not mutually exclusive, I have to actually subtract the probability of even and prime. Okay. So in this case, we have the same thing. So we have the probability of 2 plus the probability of even would be 1 out of 6 plus 3 out of 6, but that would be 4 out of 6, and that's not correct. We've only got 3 out of 6. So we would have to subtract the probability of 2 and even, which is subtract 1 out of 6, would leave me with 3 out of 6. Now the reason why we've got to do that is because this intersection is counted twice. So if we go back up to our generalization for a non-mutually exclusive event, probability of A or B would be the probability of A plus the probability of B, but subtract the probability of A intersection B, being the AND. So that's when we have to know about mutually exclusive or non-mutually exclusive events.
Why minus the 1?
Because you count it twice in all the A and all the B systems.
If you think about, let's take this one, right? And maybe if I can draw a circle. So this is, we'll do this situation. This is primes. So evens, this is primes. Alright? So even numbers on a dice are 2, 4 and 6. Okay? Prime numbers are 3, 5 and 2. Right? Now, if I were to say what is the probability of taking a number that is either even or prime, well, you would say, well, it's 3 out of 6 and another 3 out of 6, wouldn't you? But what's the problem? The problem is, if I do that, that 2 has been counted twice. And there is only 1 2 on the dice. I can't increase the probability of getting a 2 just because it counts in both groups. So that's why we, instead of drawing 2 separate circles, when we've got something in both, we have this intersection and we put it there. but then we have to remember that it's counted in both groups, so we count it once and then we have to subtract it so it's not counted twice. Alright. What's the correct notation for saying probability of A or B? So we've got probability of A and B here. Do you remember the correct notation for OR? Yeah, universal. So instead of writing OR, we have union. So that union is the OR. So when you're using Venn diagrams, that's, basically, it's as simple as that. If you kind of have one or the other, you add them together, or if they're not mutually exclusive, you have to figure out which one's included twice. If I were to say to you, though, looking at this situation, right? So actually, what is the probability of, we said, probability of even or prime? The answer should be not 1, but 5 out of 6. Right? So that's the answer there. But another thing we have to consider is what's called conditional probability. Okay, conditional probability. Now there's some certain vocab that you know is going to happen. Right. So if I said to you this, you roll a die, okay? Given that I know the number is even, right? Calculate probability of it being prime. So what does the conditional part, where's the conditional part in that?
It has to be prime.
So it has to be even is actually the conditional bit. That's the bit I know, right? So the conditional probability is a condition has already been set. You are allowed to leave school if you have done your work. All right. This one is, the condition is, I know the number is already even. So what is now the probability of it being prime? So that changes things. Right. So I've still got my same diagram. Still got my same diagram, my Venn diagram.
Is this stuff for the dice?
Yep, still the dice. I'm still on my dice. Right, we've got even and we've got prime. Right. So, prime, and we know the diagram is 1, 2, 4, 6, 3, 5. Okay. So the probability that it was even or prime was 5 out of 6. But what's the probability of it being a prime, given that I know it is even? I can understand why it's not. It will be what? 1 out of, that bit's easy. 1 out of 3. Okay, so this is the thing. Conditional probability affects, is it Julia or Sammy? Is it affects or effects?
Effects is a consequence for the effects of this. But if this is affecting,
I won't remember that.
that's the second time I've explained that.
Really?
Yeah.
Conditional affects the total possible outcomes. Just by saying, I know it is even, right? That means I am discounting completely 1, 3, and 5, so I should not even consider them. All right? So actually, I could, from my diagram, cross out those. They are no longer part of the situation. All right? So then, 2 is the only one that is left that is prime. All right? So I've only got 1 out of those 3 things left. So that's conditional probability.
So it's like the outcome of even depends on the outcome.
No, it's slightly different than having 2 things happening.
No, I just mean, like, I don't get the idea why you do division.
There's no division.
Yeah.
The fraction, the fraction is not. I've just, by saying I know the number is even, I have to forget that the odds even exist. That's all. So it's just, normally this number would be 6 because there are 6 numbers. But if I limit your options to it's only the even numbers, well, there are only, so it's not that when I roll a die I will only ever get even numbers. What I'm saying is, if I were playing a game with you and I rolled a dice and went, right, guess what's on that die? What chance would you have of getting it right? 1 out of 6. But if I rolled a dice and I said, right, give you a clue, it is even. What is the chance of you getting it right? Okay. So you've only got 3 options to choose from. So that's why, so we've got conditional probability. That is written like this, with a straight line. It's not an I, it's a straight line. Okay.
That is a straight line? Or?
That is a straight line. It's not an I, it's a straight line. You'll see it on page 85.
That's given a time. What's the probability?
Yeah. So given A, what's the probability of it being what is the probability of A being given that it is B has already happened? Because
So
we then have
even would be B.
the so this is equal to the probability of A intersection B over the probability of B happening. So it's this denominator. So B is the thing that you know has happened. So that's so in this case, B is the evenness. Yeah. So what is the probability of it being prime, knowing that it is already even? So it's a straight line. So that's conditional probability. So this at the moment is all when only one thing happens. I roll a dice once. So it's this discussion of all the probability of things happening, right? So sometimes, for instance, it's nice and easy. So what's the probability of it being a 1 or a 2 or a 3? Nice. If I said to you this other word, and, what's the probability on the dice of rolling a 2 and a 4?
0.
Yeah, you know why? Because it can't happen, right? So when I roll a dice once, so that's a simple situation. So that word and, you have to think of it very carefully when there's only one thing happening. The word or fits very well with only one situation. Okay? What's the next phase though?
Like if you roll it twice.
Exactly. So what if I were to roll a dice a second time? Right? We then have that situation. So let's stick with our dice analogy, and we say, so 2 dice are rolled. Now we can start looking for the word and fits in nicely. So if I said to you what was the probability of a 2 happening, and the probability of a 4 happening. Alright?
So 1 out of 6 times what else?
So you already know the times. So we've got the probability of a 2 times the probability of a 4. Okay. This is assuming what? Well, in this case with the dice we know, but in the event, so that simple multiplication is just the fact that the 2 happens does not affect the 4 in any way. Okay. So in this case, it is just 1 out of 6 times 1 out of 6, which equals,
Wouldn't it be 2 out of 2 out of 12, yeah.
the other way to think about it, which is where we start bringing a sample space diagram into this now, okay, is a sample space diagram is the aid of it is to help you figure out how many possible outcomes there are, because people do get it wrong, all right, initially when they don't remember the times. So the way to work it out is, you know, on a dice you could get a 1, 2, 3, a 4, a 5 and a 6. On the second dice, the same thing. So what we have to do, that helps us figure out, with the aid of a grid, how many possible outcomes there are. So getting a 1 and a 1 is one possible outcome. So if I look at this, I know that rolling 2 dice, there are 36 possible outcomes. So what is the probability of 2 and a 4? Well, I can get a 2 and a 4, and that's one possibility. But what's the other option?
4 and 2.
4 and a 2. Okay, that's why we have. Sorry, I put that in the wrong thing. Okay. So, it doesn't work. Why doesn't it work?
Because you're adding 2 out of 6 plus 1 out of 6. That makes it 2 out of 36, not 1 out of 6. Oh, isn't this, it can be either, first it can be 2, or first can be 4, and then second dice can be 2 or 4.
Yeah.
So we have to add the same thing again.
No.
So if we add like P of 2 times P of 4 plus P of 4 times P of 2. Yeah, no,
It is, because what we've got in this situation, right, and this is where the misconception does come, exactly like you're saying, because P of 2 and P of 4 is the same. We've got this word or, so we can do 4 and 2 as well. Okay, so in this situation we have to consider both options. All right, because it is more likely that you're going to get a 4 and a 2 than it is you're going to get a 1 and a 1 or a 2 and a 2 and so on, which is why in games of chance they set the high scores as double 6, you know, double 3, double whatever, because they're less likely than any other option. All right. So yes, we have that, and then we have to do plus. So we have 1, and then we also have the other one. Right? So that's how we can use our sample space diagram. What could I do with this word to change that to be only 1 out of 36?
Make it condition.
Or
Oh no, so what would be the probability of getting a 2 or a 4? That's a good question. What's the probability of getting a 2 or a 4? I could get a 1 and a 2, a 1 and a 4, a 2 and a 1, 2 and a 2, 2 and a 3, 2 and a 4, 2 and a 5, 2 and a 3 and a 2, 4 and a 2, 4 and a 1. All of these options are a 2 or a 4. Do you understand the difference? Okay? So that word or, like the word union, brings lots of options together rather than limits them. Right? The word I was thinking of that limits it further than what we had from the 2 is, what if I said a 2 then a 4? Or like you said, what if I make it conditional, like I know the first dice was a 2, what is the probability the second one will be a 4? Well, so it's different. So you have got to be aware of the vocabulary of it.
What we were talking about was the 2 then 4. Just one obviously it's not what we say.
Yeah. It should be 1 out of the 36. The question then comes is, if I roll both dice at the same time, what's the probability of getting a 2 then a 4? Because theoretically it's still 1 out of 36, you know. Depends which one you want to take as the first dice and which of those, you know. So we've got to be a little bit careful, and the questions are written carefully that they don't necessarily confuse you like that. It's like if I change the question, it's not dice, it's coloured counters in a bag. You pull one out. You know, if I pull one out and then pull another one out, is that the same as just pulling 2 out at the same time?
No, because before now you lower the size, so it would be
Depends. It depends. Yeah.
Oh, how would you put it? That would be a question.
Right, so we'll come on to this bit next. So this word, and when we've got 2 events happening, we start with then the multiplying, but you do have to consider that there are more than one way round of doing things. So it's not as simple as just going, oh, 2 then a 4. You have to do 4 then a 2. Okay? Right? If I said to you, what was the probability of getting 2 numbers the same? Six out of 36, because it's a 1 and a 1, or a 2 and a 2, or a 3 and a 3, and so on. So you do 1 out of 36 plus 1 out. So you can either do it with just purely maths, or you can look at your diagram: 1 and 1, 2 and 2, 3 and 3, and so on. So our sample space diagram is quite useful in that. What's the problem, do you think? What's the limitation with a sample space diagram?
Get a lot of numbers.
Well, I can still do it. I mean, it is kind of, I can still use it. Is there any time, you know, that's a kind of limitation, but not really a limitation, you know. But there is a point at which sample space, you can't use it.
If the sample space changes, like when you use it for now,
Maybe. Yeah. Still looks at all the possible options though.
Maybe if one dice it goes to 6 and the other one maybe goes to...
No, but still add it on, that's not a problem.
Probability of one of them is dependent on the
I think that's what we said, but it really, a sample space diagram is just a way of listing all possible outcomes rather than, so it makes it more difficult with conditional probability because it does change, yes, you're right, but there's also a much more obvious way of when sample space becomes useless.
If
you add a dice.
If I add another dice. How do you list the outcomes for 3 dice? So you could work in 3 dimensions, couldn't you? So 6 by 6 by 6. If you think of a cube, the corner of a cube, right, that would give you the number of outcomes. But then I could add a 4th dice, and then you're like, then it just becomes a purely mathematical process, yeah, of working out the number of outcomes. But so a sample space diagram can be used simply to list the outcomes. It makes it easier. And again, if I said to you, what was the probability, you know, of getting a 3 and a 4, or two even numbers. Would that help you with this whole mutually exclusive thing?
Wait, 3 then a 4 or
So
3?
a 3 and a 4, or two even numbers. So again, with a sample space diagram, you go 3 and a 4 would be here, so one option, also a 4 and a 3, and then we go for two even numbers would be 2 and a 2, 2 and a 4, 2 and a 6, 4 and a 2, 4 and a 6, 4 and a 4, and so on. And you could list all the, and then 6, 2, 6, 4, 6.
Mr. Bob,
Yeah.
what would be the formula be for the probability of 2 or 4 for 2 dice? How would you calculate?
Well, when we've got more than one event, like you said, it's the probability of A. Where's my thing? So it's just what we've got here. The probability of A times the probability of B, but you'd have to add however many times it happens.
If it's like 2 or 4.
2 or a 4.
Yeah, for
Um,
2 dice. Because you said like there are lots of possibilities. There's
yeah, so like,
over
but
2
you'd
and
have to
1.
know how many times it can happen. You see. So like you said, it's
Oh.
work out the probability happening once and then figure out how many. So maybe I could write that it's times the number of times it happens, because it's always going to be the same. To be honest, guys, this gets a lot easier when we start dealing with tree diagrams. It's a much nicer way of doing it. But yeah, like I said, it does. Sample space kind of stops working when you have more than two things. But let's have a quick look. What was it I was going to? Two types of problem that we need to be aware of. The reason why I'm going through this quickly, guys, even though you two are getting bored in the chat, is that most of you it's first, second, third time through. We've got these two types of problems. Non-replacement, okay, or replacement type problems. Right, excuse me. So this non-replacement is a branch of conditional, again, conditional probability, where the probability of the second event is affected by the probability of the first event. Right? And a replacement problem is when it doesn't. Now, sometimes it's stated in a question, sometimes it's not, because it's obvious. So, for instance, I've got counters in a bag. I pull a counter out, I look at the colour of it, what's the probability of it being whatever. Put it back in the bag, pull out another counter. What is the probability of it being the same colour, or the probability of it being, and so on. Okay, so that would be a replacement problem. Now, the probability of the colour coming out each time never changes. Alright? It's like the National Lottery thing, or the Euro Millions, or whatever. Those people that change their numbers every week because they think it won't happen twice, right? The probability of that number happening every week, it doesn't change. It's just so small, it's not likely to happen that way. The non-replacement questions, it might say the counter is taken out and not returned and put back. Then you pick another one. What's the effect of the problem if I do that?
The number of total possible outcomes.
Yeah, exactly. The number of total outcomes reduces. And it also depends on what was picked out before. So if the probability of picking a blue out depends on whether I picked a blue out before or not. Because if I did, there'd be less blues. If I didn't, there'll be more blues than anything else. So we've got that to consider. Now, some problems are not stated replacement or not because it's obvious. Like, I take two out at the same time is a non-replacement problem. But what if I say I want to choose 2 people from a room. What is the probability that I pick 2 boys? Right? So if I'm picking people to go and do something, will I go in, pick a boy, and go, okay, I've got a boy, right, go and sit back down, right, now I'm going to pick another person. Would I ever do that? No, I'd go, right, you come out, right, now I pick you come out, and so on. What's the probability? So that's a non-replacement question, but it will not be stated as non-replacement because you have to use a bit of common sense. Right, so there are problems like that. Okay, next time we'll have a look at the tree diagram stuff. Make sure you're happy with the Venn diagram stuff. We'll move through this quite quickly.